Welcome to the wonderful world of physics. This is Chapter 7 on oscillations. This chapter will introduce oscillatory motion. Nature and technology provide many examples of periodic motion, motion that repeatedly follows the same trajectory. Uniform circular motion, such as the Earth in orbit around the Sun or the Moon in orbit around the Earth, give a good example. We can also think with motion that repeats the same trajectory, molecules as they vibrate back and forth. We can think the walls of the heart as they contract and expand. A leaf that's on a pond will go up and down with the waves, and a pendulum going back and forth. And this study of periodic motion will lead us to, in Chapter 11, the study of waves, and that will lead us to thinking about sound and music and light. I want to define the period for periodic motion is the time to complete one cycle through a full trajectory. So, for example, the Earth going around the Sun, its period is 1 year. The frequency is the reciprocal of period. So if period is seconds per cycle, frequency is cycles per second. The units we use are 1/seconds because we often don't write cycles as a unit. So even though we say cycles per second, we might write it out as seconds to the -1. Although the preferred unit for cycles per second is 1 Hertz. And since it's named after a man, Heinrich Hertz, we do not capitalize the H on Hertz, but when we abbreviate it, we do capitalize that H. So frequency is the reciprocal of the period. Again, think if period is seconds per cycle, frequency is cycles per second. Let's look at an example in the book. Example 7.1, it says Earth orbits the Sun every 365 days. Find the frequency of this motion in Hertz. And then part B says a tuning fork set to concert A vibrates at 440 Hertz. What is the period of its motion? So for question A, we're given the period, we want to find frequency. And as long as we have MKS units, so make sure it's in seconds, then it should be okay. So frequency is 1/, and here we have how many seconds are in a year, 3.15 times 10 to the 7th. So we get a frequency for the Earth going around the Sun of 3.17 times 10 to the -8 Hertz. Question B gives the frequency. We need to find the period. And so the frequency is given as 440 Hertz, and that is in terms of seconds, because remember, a Hertz is a cycle per second. So the period is 1 over frequency, so 1 over 440 Hertz, and that gives 2.27 times 10 to the -3 seconds, or 2.27 milliseconds for the period. Down below in this animation, you can see a tuning fork. We'll get more into this in Chapter 11 when we talk about sound, but it's the vibration of that tuning fork on the millisecond level of timing, the vibration in and out that causes high and low air pressure waves, and this is sound. Section 7.2, simple harmonic motion. You can see in the graph, this is a graph of what's called a sinusoidal oscillation. It's a sine curve. It could also be called a cosine curve, and actually what I've drawn there is a cosine curve. And keep in mind, a sine curve and a cosine curve are the same shape. They're just offset a little bit from left to right. And this can mimic the mass on an ideal spring, assuming the mass is on a frictionless surface. So here you see in the animation down below, it is oscillating back and forth in that sinusoidal motion. With the sinusoidal oscillation, as you can see in the graph, its position versus time curve has the smooth undulating shape of either sine or cosine curve. And a system, such as what you see with the spring and the mass, whose motion describes a sinusoidal function of time, is called a simple harmonic oscillator. and its motion is simple harmonic motion. And we see simple harmonic motion a lot in nature and in technology. Let's consider that mass on a spring, and we'll consider it gliding back and forth on a frictionless surface. And there you have on the picture, there's the mass. Right now the spring is at equilibrium, x equals 0, so it's going to oscillate back and forth. The distance it's going to go from equilibrium is going to be a distance of a. And by the way, I use the letter a because a stands for amplitude. It's going to be the amplitude of that sine function. So it's going to go as far to the left as negative a and as far to the right as a. And remember, when we're dealing with a spring, there's a restoring force known as Hooke's law. The force is negative k times x. K is the spring constant. And the negative sign just refers to the fact that the restoring force is going to be opposite from displacement, meaning if the mass were over here in the positive direction, the restoring force would be in the negative direction. If the mass were over here and the spring were compressed, the mass is over in the negative direction, the restoring force would act to shove it in the positive direction, always bringing it back to equilibrium. So A, known as the amplitude, is the maximum distance from equilibrium. Now let's say we take that mass, we pull it out to position positive A, and then we start the timer and release it. So it's at position A when t equals 0. You can see the graph down below. That would give a cosine function. It'll start up here at A. At time equals 0, it'll go into negative territory down to negative A, up to positive A, and there it would have completed an entire period. And this can be modeled mathematically by a cosine function, x equals amplitude times cosine of omega t. Now omega is the frequency, but it's not F. It's not cycles per second. It's actually in radians per second. So there it is, the graph with the formula, x equals a cosine omega t. Omega, as I said a minute ago, is the angular frequency, and it is 2 pi times the frequency. So if frequency is cycles per second, omega is radians per second. And since there are 2 pi radians in every cycle, think about the unit circle. Going around a circle once is 2 pi radians. So omega is 2 pi times the frequency. The units are radians per second. Now, radians are considered a pseudo unit, meaning they don't measure any physical direction or dimension. It just refers to how many times how many iterations something has gone through a cycle. And so in our equations, as we do dimensional analysis, sometimes the radians will be there, but sometimes they'll just, like a ghost, kind of disappear. So get used to seeing it both ways. Omega is radians per second, but sometimes just think of it as per second, or seconds to the negative 1. Now, if omega is 2 pi times the frequency, and remember frequency is 1 over period, we could also have this relationship that omega is 2 pi over period. So it's 2 pi radians divided by the time for one cycle. Now think back to our mass. Let's say we pull it out and we release it, and we don't start the timer until it's gone back into negative territory, and then it's coming up towards positive. And imagine, so it's out here, and we release it, it goes in, and then right as it's crossing equilibrium, we start the timer there. Then we'll have a graph like what you see down here to the right. It's a sine curve. And as I said before, a sine curve and a cosine curve are the same shape. It's just they're offset by a quarter of a cycle from each other. So sometimes you'll see it as a sine function, sometimes as a cosine function. This motion back and forth can be modeled mathematically either way, sine or cosine. And so there it is, x equals sine omega t, matching that picture. So once again, let's say we start it at this mass, and you've seen this before when you first learned about springs. You know that it's got a restoring force. If it's out at position A, then the restoring force to the left is F equals negative KA. Now, as it's going to oscillate, or you just think as you're holding it, we haven't released it yet, it has a speed of 0. And it's going to go, once we release it, to the left and to the right, and once it comes back here, you know it'll have a speed of 0 again because it's oscillating. And we can also quantify its acceleration, lowercase a, by Newton's second law. Acceleration is force divided by mass. So at this moment, its acceleration is negative k times amplitude divided by the mass. So we let it go, and then it's speeding up because it's got that negative, that leftward acceleration. Right at equilibrium is going to be where it's at its fastest. Because once it passes equilibrium, it's no longer being accelerated to the left, and in fact, it's going to get an acceleration to the right. The spring, in being compressed, is going to try to slow it down. So right there in the middle at equilibrium, it's at its fastest speed. Right at that moment, it's got a force of 0 on it. The restoring force is 0 because it's at equilibrium. And it's going to cruise through, slow down, slow down, slow down, and make it all the way to negative a, and that's its turning point. At this point, it's got a restoring force of positive Ka, positive meaning to the right. It's at a speed of 0 because that's its turning point. And by Newton's second law, its acceleration is force over mass, which is Ka over m. And as it oscillates back and forth, it's going to go here, back, left, left, right, left, right. It is trading off between potential energy and kinetic energy. So when it's at either the extreme points, position A or negative A, it has no kinetic energy. It's not moving, but it's got the highest potential energy. When it's in equilibrium, right there, it's got no potential energy, but it's got the highest kinetic energy. So it's trading off between those. If we set the energy at position 1, meaning at A, and the energy at equilibrium, so we'll call that state 1 and state 2 equal to each other, and we can do that because of conservation of energy, we get this, 1/2 Ka squared. So at position A, it's all potential energy, 1/2 Ka squared, equals the energy at position 2 at equilibrium, it's all kinetic energy, so 1/2 mv squared. And since we've already recognized that's the maximum speed, let's call that V max. And then we can go through the algebra and solve for the maximum speed of this oscillator. So we can say the maximum speed is the amplitude times square root of K over M. Now let's think conceptually about what that means. How fast can we get this thing going? Well, first of all, we recognize that it will be at its fastest when it's in the middle. And the speed is going to be related to the amplitude, first of all. So the farther out you pull it, the faster it'll be going. And then it's related to the stiffness of the spring. The stiffer the spring, the higher the K constant, the faster it can be going. But that's going to be offset by the mass. Remember, mass is an object's ability to resist accelerations. So if it has a high mass on it, it's not going to want to go as fast. It's going to be resisting those forces. The examples I've used so far have been a horizontal spring with a mass gliding on a surface, but we needed a frictionless surface. It's easier to avoid friction if you hang the spring vertically to get a simple harmonic oscillator. And so if you look at here, we've got a spring, let's hang it from the ceiling, and now we hang a mass on it. This becomes the new equilibrium point. So the weight is going to pull down, and the heavier it is, the more it's going to extend it from the original equilibrium point. But for oscillation purposes, this becomes the new equilibrium point. So we can pull it down to A, and it's going to go up and down around that equilibrium point. Gravity does not significantly affect the oscillator. Gravity only changes the equilibrium position once we put the mass there. But once that is the equilibrium position, gravity isn't going to affect the oscillator. Oscillations about the new equilibrium occur exactly as they do for the horizontal oscillator. That's because the force of gravity is constant, while oscillations result from the varying force of the spring. So that means that the period, t, for the vertical oscillator is the same as it would have been for a horizontal one. Now, these equations here, I give them to you without derivation, and the book doesn't derive them either. But we can see that the period for a harmonic oscillator is 2 pi times the square root of mass over k. And think about what that means. It means that the greater the mass, then the longer the period, because the mass being more resistant to forces is going to not be whipped around so easily. So it'll have a longer period. And period can be shortened by a stiffer spring. That stiffer spring creates more forces. Frequency, I want you to remember, is just the reciprocal of the period. So take the reciprocal of period and you get 1 over 2 pi times square root of k over m. Now, this is for an ideal spring, and part of the being an ideal harmonic oscillator with an ideal spring is that the mass of the spring is negligible compared to the mass hanging off of it. And so that's the only kind of case we'll consider in this class. We're going to neglect the mass of the spring itself and just be concerned with the mass that's hanging on the end. Remember also, if we want to talk about the angular frequency, that's 2 pi times the frequency. So if you take f, multiply it by 2 pi, it gets rid of that 1 over 2 pi. So omega is square root of k over m. The interesting thing in nature is that you don't actually have to have a coil of metal that we call a spring for this equation to work. There are many things in nature that oscillate. I've mentioned before a spider web that vibrates when something lands on it, the walls of your heart as they contract and expand. Many things in nature are mathematically modeled by these equations. And whereas in those cases there's K, but it doesn't refer to the stiffness of the spring. You can still think of it as the stiffness of the oscillator. Now, as you look at these equations, it's interesting to note how amplitude relates to period and frequency, and you can see amplitude doesn't come up in these equations. It doesn't relate. So if you think about this oscillator, going up to this vertical oscillator, you can pull it down a little bit, pull it down just a few millimeters, and it'll oscillate at one period. And then take it, pull it down several centimeters, and it'll oscillate with the same period. It'll go faster, but the period is going to be the same. So period and frequency are not affected by amplitude. Let's look at, in the back of the chapter, problem number 38. Give us some practice using these equations. It says a mass spring system has K equals 55.2 newtons per meter. Mass is 0.450 kilograms. Find the frequency, angular frequency, and period of its simple harmonic motion. So I've listed out the given information, or I've written out the information. I've listed out what we need to find. And here are the 3 related equations. So we're just going to use those equations. We have K and M, and we can just plug those in. And I encourage you to do that. Maybe you want to pause the video and do it on your own and see that you get the same answers that I get on the next page. And here we go. For frequency, we're going to use this equation on the left. So 1 over 2 pi times k, square root of k divided by m, 55.2 divided by 0.450. You can do an exercise in dimensional analysis and convince yourself that these units, newtons per meter per kilogram, do come out to hertz. We get 1.76 hertz. For omega, It's really just frequency times 2 pi, but we can also use the equation at the top of the page here. Square root of k over m, we get 11.1 radians per second. And finally, period, you can use this lengthier equation, or you can do 1 over the frequency. Might as well do both and make sure you get the same answer, but we get 0.567 seconds. Let's look now at problem number 43. It says a mass spring system has mass 0.97 kilograms and oscillates with a period of 0.5 seconds. Find the spring constant. And before we get into this, I want you to note that both in this problem and number 38, the problem didn't distinguish between whether it's horizontal or vertical because it doesn't matter. It's just a mass spring system. Here I've listed out the given information and shown what we're looking for, k equals. And given that we have the mass and the period and we want to know k, this looks like the appropriate equation to use. Period equals 2 pi times square root of m over k. Let's go through the algebra. So step by step, we're going to get that k by itself. I'll start by dividing both sides by 2 pi. Now we've got that square root to get rid of. So on the last line of the page, we're going to square both sides. We now have t over 2 pi, all that squared, equals m over k. There it is again. Let's get rid of that m by dividing both sides by m. So 1 over m times t over 2 pi squared equals, and we're left with 1 over k. Be careful with the algebra, that k was in the denominator, so you can't just wipe away the m and be left with a k. You're left with 1 over k. My last step then is to take the reciprocal of both sides of the equation. So flip both sides. K equals m times the square of 2 pi over t. And you should get k is 154 newtons over meters. And again, it could be a good exercise in dimensional analysis to convince yourself that when you have kilograms and over seconds squared, that's going to come out to newtons per meter. I'm going to skip a few sections in the book and move on to a special application of simple harmonic motion. And this is now section 7.5, the simple pendulum. About 4 centuries ago, Galileo noticed that the oscillation period of a swinging chandelier seemed independent of the amplitude. He decided that meant a pendulum would make a good timing device. Galileo then used pendula as timers in kinematic experiments. Pendulum clocks appeared soon after Galileo's time, and they have been around ever since. So here you have this excellent timing device of a pendulum. And what we're going to see, actually, we think of a pendulum as being a simple harmonic oscillator. It's approximately a simple harmonic oscillator. So sometimes physicists call it a simple harmonic approxilator. It's approximately an oscillator. All right, so a simple pendulum is a mass. We'll treat it as a point particle because it's going to be a significantly small mass that's suspended from either a cord or a rod. Now, this cord or rod is going to have a length of L and negligible mass. So as long as we can consider that the mass of the pendulum is all located at the mass that's hanging on the end, which we call a bob. A real physical pendulum will approximate this if the size of the bob is much, much smaller than the length. And so you can see my picture here. The mass of the cord is much, much smaller, meaning it's negligible compared to the mass of the bob. And the cord or rod remains straight and a fixed length. So it can't be a rubber band or something stretchy. Now, as it goes back and forth, here I've drawn half of the arc. It's going to swing out to some angle theta. And it's going to follow this arc length, and then it'll swing out to the left side. But down in the middle where my pointer is, my red pointer, that's the equilibrium position. I've made the arc length letter S because that's what we did in trigonometry class, the arc length going around a part of a circle is S. So it's a circular arc of radius L, which is the length of the string. The arc length is S equals L theta. As long as theta is in radians, this is a basic trigonometric equation here, or going around a circle, or the arc of a circle. The arc length equals the radius times the angle in radians. There's the picture again. And now let's think about the forces that are acting on this bob. And even though it seems very different from a mass on a spring, we're going to see some similarities. So with a spring mass system, it is the restoring force, F equals negative kx, that brings it back to equilibrium. For a pendulum, it's gravity that brings it back to equilibrium. Let's consider this bob. The two forces acting on it, there's the tension in the string that's pulling it up, and in this case to the left. There's gravity that brings it straight down. We're going to consider, kind of like we did motion on an incline where we rotated the x and y coordinate systems, we're going to think, you can look at my purple vectors, of the forces that are perpendicular to the string and the forces that are tangential to the string. So there's my purple vectors there. The force tangential, I'm sorry, a minute ago I said tangential to the string. I meant tangential to the arc that it's traveling. The force tangential to the arc, which is right here, that's going to be the force that's going to bring it to equilibrium. And that is mg times sine of theta by the trig of this right triangle. And let's throw a negative sign in there because it's pulling it opposite of displacement. So if we think it is right now displaced to the right in the positive direction, the force is pulling it down and to the left. So that's why we throw that negative sign in there. So the force tangential, or along the arc, I'll just call it F sub s, is negative mg sine theta. Now I want to compare that with, for a simple harmonic oscillator, F equals negative kx. And look at the contrast and comparison. For a simple pendulum, it's negative mg times sine theta. For the harmonic oscillator, it's negative kx. We have, first of all, the negative sign. Secondly, we have a constant that has something to do with the force that's bringing it back to equilibrium. In the case of the pendulum, it's the weight of the bob. In the case of the mass spring system, it's the stiffness of the spring. But in both cases, it's negative and then a constant. And then look at what I've circled in purple here. This is why a pendulum is not precisely a simple harmonic oscillator. A simple harmonic oscillator is defined as, come over here to the right where my pointer is, it's defined as where the restoring force is proportional to displacement, such as F equals negative k times x. Here, it's not proportional to displacement, it's proportional to the sine of the angle. However, and now I'm going to get into where we can approximate it as being proportional to displacement. We're going to use what in math is known as the small angle approximation. For small angles, as long as you're doing it in radians, not degrees, theta is approximately equal to sine of theta. And you can try that in your calculator. You can make sure, first of all, that your calculator is in radians mode. And if you take, for example, the sine of 0.1, it is 0.0998. So it's pretty close to 0.1. If you take the sine of 0.04, it's 0.03999. So for small angles, it's very, very close. As long as the pendulum does not swing out very far with a large angle, then this equation, that the restoring force is negative mg sine theta, can be approximated as negative mg times theta. Now, remember the relationship that arc sine is length times theta, or radius times theta, really. So theta is going to be the arc length divided by the length of the string. And so I'm going to replace theta with S over L. And now we have this bottom line equation here. Now, if we've made that small angle approximation, now it looks like a simple harmonic oscillator because the restoring force is negative times mg over L. Now that's just a constant based on the physical parameters of the pendulum, but times S, and that is the displacement, the arc length. So let's keep the angle small. Practically speaking, we're going to keep it under maybe 15 or 20 degrees, and it's close enough to a harmonic oscillator. You look at the animation down below, and that blue pendulum is very, very far out. So the farther out it gets, it's going to be less of a harmonic oscillator. The one in the middle, the brown one, that's pushing the edge of acceptable. Now, this animation is actually showing that they all have the same timing. But then again, it's just an animation. In reality, if you give it enough time, the blue one will be a little different from the black one. So here we have it that the restoring force, this is from the previous page, is negative mgs over L. We can now think what the acceleration is, the force divided by mass, and that becomes negative g over L times s. So negative the strength of gravity divided by the length of the pendulum times the arc length. Compare that with, for a simple harmonic oscillator, acceleration is negative k over m times x. So as you do that comparison, you can see that for a harmonic oscillator, my green equation here, that the thing that will increase acceleration is a stiff spring, represented by K. Corresponding to that with a pendulum, it's a strong gravitational field. Stronger gravity, that depends on what planet or moon you're standing on, is going to have a quicker acceleration. And it's offset by, in the mass spring system, the mass. So the greater the mass, it's going to resist those accelerations. The corresponding offset is for a pendulum, it's the length. The greater the length, then it's going to not accelerate as much. So what we see is that for a pendulum, acceleration is proportional to displacement. Not just for a pendulum, but any simple harmonic oscillator. The more you displace it, the more acceleration there's going to be. For a pendulum, G, strength of gravity, acts like the spring constant. The length is acting like the mass. And so if we take our equation that you've already learned for a mass spring system, period is 2 pi times square root of m over k, and replace mass with length and k with g, we have this is your main equation for a pendulum, that the period is 2 pi over square root of length times g. So there it is for a simple pendulum. These two equations are the main ones you're going to use for a pendulum. Period is 2 pi times square root of length over g. Frequency is the reciprocal of that, so 1 over 2 pi times square root of g over L. And also remember that omega is frequency times 2 pi, so the angular frequency is square root of g over L. And again, compare that with what you've learned previously for a mass spring system. Omega is square root of k over m. The k is replaced by the g, the m is replaced by the L. Let's look at an example that's in the book. This is example 7-8. It says, how long should a simple pendulum be so that its small oscillation period is 2 seconds? And then, if you took this pendulum to the moon, where g on the moon is only 1.60 meters per second squared, what would its period be there? All right, let's answer the first question. The period is 2 seconds. What is the length? Here's the period equation. Go through the algebra, dividing by 2 pi, squaring both sides, multiplying by g, and after about 3 steps, you get that the length is t over 2 pi squared times g. So make sure you can work through that algebra to get to length. And we get a length of 0.993 meters. Question B says, now what if we have that pendulum with a length of 0.993 meters, but we take it to the moon? Well, with the moon's weaker gravity, it's only 1/6 as strong as Earth's gravity, that pendulum is going to be going more slowly. So let's do the period equation, but instead of g being 9.80, it's going to be 1.60. So we're going to plug in what we got for the length, taking it out to more digits, it's 0.9929476, that's what I got up here, divided by 1.6, and we get a period of 4.95 seconds. So much slower than the 2 seconds it would be on the Earth. Now, a neat technique, and the more you stick with physics, the more you'll see different techniques for solving different problems. Here's another way to solve question B. And the neat thing about this next technique is we don't actually need the length of the pendulum to solve question B. If all we have is the period on Earth and the different strengths of gravity between Earth and Moon, we can solve directly for the period on the Moon without actually needing that intermediate step of figuring out the length of the pendulum. So follow me on this, please. Let's first set up a ratio. Period on the Moon divided by period on Earth. Now you'll see where this is going as we go through it. Eventually we're just going to solve for period on the Moon. And in the numerator is the period on the Moon, 2 pi times square root of L over G on the Moon. In the denominator is period on the Earth, 2 pi times square root of L over G on the Earth. Now we're going to use the magic of algebra. We're going to see anything that divides out, we're going to make it divide out. So those 2 pi's in the numerator and denominator, they divide out. The let me back up. The length of the pendulum in the numerator up top and the length of the pendulum in the numerator down below, they will divide out. All you're left with is square root of 1 over G on the Moon over square root of 1 over G on the Earth. Now be careful, those are both reciprocals. So work through it, and I didn't write out the intermediate steps, but you should be able to see that because those are reciprocals there, you're left with the square root of G on the Earth over G on the Moon. And that's it, that's the ratio of the periods. So period on the Moon equals period on the Earth times square root of G on the Earth over G on the Moon, because if we go back up to this equation, I've multiplied both sides by period on the Earth. So we're left with this, and now we can plug those in, and you can see the beauty of this is we didn't need the length of the pendulum. It just becomes 2 seconds times the square root of the ratio of those strengths of gravity. So 4.95 seconds. And that is the end for us on Chapter 7, Oscillations. Have a great day.